in general, thanks to everyone for inviting me or having me here to talk about our work. So this is a joint work. So again, I'm George Fletcher from Eindhoven in the Netherlands. So this is joint work with folks mostly in France, so folks in Lyon and Lille, and also folks in Oxford and with my student in Eindhoven. So I'll skip all the motivation and just jump right to what I'm going to present. So today I'd like to briefly talk about some work that we've been doing over the last year or so on gMark. So it's an open source framework for generating synthetic graph instances and synthetic query workloads coupled to those instances, right? So query workloads that make sense for the instances that have been generated. So the particular focus of gMark has been to tailor, say, diverse graph data management scenarios, in particular those which are driven by query workloads. So for example, situations where you want to study problems, so solutions for, say, multi-query optimization, or, say, mapping discovery and query writing in data integration systems, or, say, workload-driven physical design and physical tuning of a database engine. And in general, our hope is to support flexible specification and generation of diverse workloads for addressing particular experimental studies, right? So kind of like an agile tool for driving the design and execution of an experimental study for a particular problem under investigation. So, so in a nutshell, what we do is, given a graph schema, gMark generates synthetic instances of the schema of some desired target size, so some desired output size, and generates query workloads with targeted structure and runtime behavior, which holds for all instances of the schema. Right? So we want to reason about the behavior, the difficulty of particular queries on arbitrary instances which are run off of the given schema. And so why gMark? Why another tool for generating synthetic instances and queries? So what we do is, well, we want to target what I mentioned, so our principles in the previous slide. So when we went to design gMark, we wanted to essentially adopt these successful aspects of the state of the art. So for example, like the Waterloo diversity benchmark, gMark is schema-driven, right? So this allows us to, say, finally tailor our graph instances for specific application domains, and also allows us, unlike actually the WatDiv benchmark, to tightly control generation of query workloads, right? So really kind of pinpointing the types of workloads that we want to study on instances of this schema. And like the LWC social network benchmark interactive workload, we wanted gMark to support the focused stress testing of query optimization choke points. And so we do this through permitting fine control of query parameters, and in particular fine control of the selectivity, right? So the asymptotic runtime behavior of the queries in our workloads. Okay, so in addition to this, some new features which we introduced in gMark. So we really wanted this for the study of graph-intensive systems. So we wanted to extend this, the state of the art, with support for flexible generation of query workloads, including graph queries, so in particular recursive path queries, which are arguably fundamental for graph analytics. And also, again, to reason about selectivity, so estimating selectivities of queries in our workload in a purely instance-independent, schema-driven fashion. Right? So this is then more scalable because all of our reasoning is on this very small object instead of a potentially very large object. It's more predictable because it's actually reasoning about the structure of any valid instance of the schema. And it's also easier to understand and explain the behavior of the query because you're explaining it in terms of the structure of these instances. All right, so in the rest of the talk, I just want to give a brief overview of the workflow of our framework, so the gMark framework. So just very quickly, we'll talk about the pieces as we go along. So as input, we have a graph schema. We'll also call this a graph configuration, which has many different parameters which can be set for the instances which are run off. And we also have a configuration for the workloads, where we have lots of different parameters that we can set for the features of the queries that we're going to synthetically run off on this schema, right? And so what we'll do is we'll generate instances and our query workloads and some sort of internal representation. So we do actually a lot of the internal work using XML tools. Nice use of XML here. And then we have a final step, a translator, which runs these queries off in particular concrete, say, practical syntaxes, such as Cypher or Sparkle. Okay, so let's talk about the first top part, the graph generation part of gMark. So going from a graph schema to instances of the schema. So the user in gMark can specify in the graph schema, well, the number of nodes to be generated in this instance. Node types, so this is a finite set of node labels, essentially the classes of nodes in our graph. So we can think of, say, author nodes, citation nodes, and journal nodes, if we're talking about a bibliographical scenario. Edge predicates, so these are a finite set of edge labels that are holding between typed nodes, right? So for example, journal papers are authored by authors, right? Or papers reference other papers, right? So things like this in this bibliographical scenario. And then we can define constraints, so the desired structural properties of these nodes, typed nodes and edges holding between them, typed edges holding between them. So for example, we can have schema constraints, so the proportion of nodes and edges of a given type, like 20% of all nodes are authors, or we can say there are a constant number of a particular type. For example, there's 100 countries. This holds for any arbitrary instance of the schema. There's always 100 countries. And then we also can constrain the structure of the predicates holding between instances of the node classes, right? So we do this by specifying the degree distributions on the in and out degree of edge predicates. And so currently we support 3 distributions, so uniform, normal, and Zipfian. So we can specify things like the out distribution of the authored by edge. Right, so papers are authored by authors is Gaussian. So typically there's on average 3 authors on a paper with some standard deviation. Right. Here's another example of another schema. So we had a student look at the Uniprot schema. It was easy because the RDFS schema is available online. So we looked at the node types and edge predicates. We actually dropped a lot of the rarer ones, so we just chose like the top, I don't know, a couple of dozen most popular node types and edge predicates. And then on that subset of the Uniprot graph, actually measured the frequency and the distributions on these edges. So we found that 35% of nodes in Uniprot are genes, 31% are proteins, 20% are authors, and so forth. And the majority of edges in Uniprot are about authoring of papers. So 64% of the edges are about people authoring papers. And then we have biological relationships, like, say, genes being encoded on, or genes or proteins occurring in objects, and also some more bibliographic citation information, like citations being referenced by. And we found so just an example of some of the distributions on the edge types. So the encoded on edge from proteins to genes has a Zipfian out distribution, in distribution, and a Gaussian out distribution. So for example, and say proteins occurring in organisms is a Zipfian in and uniform out. Okay, so how difficult is it now, given a graph schema, to generate a valid instance? It turns out it's impractical. So you can encode your favorite NP-complete. Say we just took the standard satisfiability problem. You can encode it as a graph schema, and then looking for an instantiation of that schema involves solving that problem. So yeah, so in general, given a graph configuration G, deciding whether or not you can even generate a valid instance of it is NP-complete. And as a corollary to this, also generating a workload satisfying a graph workload configuration, a graph configuration is also intractable. So what we do, we want this to be a practical tool, right? So in particular, all of our algorithms should be linear. So we kind of take a best effort approach of generating instances and query workloads, in which essentially we, up to some certain point, we try to, as long as it doesn't require backtracking in the generation, we satisfy the constraints, so the distributions of edges, and then when we run out, we just kind of, it just fails at that point. Yes?
Can you elaborate why it would be intractable to generate these? I mean, just generating a particular percentage of node types seems like intractable.
Yeah, so it has to do with satisfying the degree distributions on the edges. And so essentially you can encode like true and false, and then you have to, you can encode that for each of the satisfiability clauses. You have to find some way of assigning true or false to each of the it's the existence of a true or false edge, and then for each of the individual variables, and then a true or false edge for each of the conjuncts. So you can just encode it as satisfying a distribution.
Yeah, because I thought that I understand that there's no attempt made like in the previous talk to really have clustering coefficients or kind of more complex graph to satisfy more complex graph metrics. So I thought these metrics are relatively simple, but you say already with the average degree, it's already intractable.
Yeah, with these three types of degree distributions, you can already encode essentially a choice between true or false, and then you just encode your structure in that choice. Okay, so just practically speaking, so in general it's intractable, so we have kind of this best effort approach to satisfying the schema constraint. So we took off the shelf, currently kind of the state-of-the-art popular benchmarks and tools, and we adapted them to meaningful gMark configurations. So some features we support that aren't supported in some of these benchmarks, and vice versa. So we kind of did a best effort encoding of these, and also adding say new gMark features. So our default is just a bibliographical kind of citation, author, paper network. We also encoded the social network benchmark schema. The default schema that ships with the WattDiv benchmark is kind of an e-commerce sort of scenario. And also SP2 bench, which is a very popular Sparkle benchmark, which is a fixed kind of DBLP, also a bibliographical sort of schema use case. Okay, so just how scalable is this? So these are numbers of generation times varying, so increasing the graph sizes. And this is just on a machine like my laptop here. It's the student's laptop, probably a little bit beefier than a MacBook Air, but still not a special machine. So in general, we can generate up to hundreds of millions of nodes. So this is now talking about hundreds of millions or billions of edges. For most of the use cases in a matter of minutes or tens of minutes. There is one, so the WattDiv was particularly challenging because it's a very rich and also very dense schema, which has, I think, 2 orders of magnitude higher number of edges than say our default bibliographical use case. And there we are up to in the hours, so a couple of hours to generate a graph with billions of edges. So we didn't spend a whole lot of time engineering this to making sure that it was super efficient or anything, but already in kind of this good enough implementation, I think these are practical numbers for running off instances of schemas to do some sort of experimental study of an algorithm under test. But definitely, so we have a student now actually improving the engineering of this and adding further features to the graph instance generator. And so the challenge is always to keep the numbers within this sort of ballpark or even better.
Student also considering doing these more advanced features, like looking at more complex graph characteristics.
Yeah, definitely. That's his mandate.
And also like the value distributions and the correlation between value distributions.
Yep. Yeah. So it's also he has kind of a very difficult mandate. But yeah, essentially his job is to add these sort of more sophisticated features which don't exist in this first version of gMark. Yeah. Okay, so that's instance generation. Let's look at query workload generation. So input to this process is both the graph schema, because we're generating queries on a schema, and then a configuration of what we want in our workload. So the query language internally for us, so the logic that we're using is the so-called unions of conjunctions of regular path queries. And so we chose this because it's kind of a lowest common denominator. There's lots of bells and whistles that you can add on top of this, and we're also considering to add on top of this in future releases. But it's a kind of a good starting point. So these are the core constructs of, say, Sparkle 1.1, also Oracle's PGQL, and also Neo4j's OpenCipher. The core construct there is a conjunctive regular path pattern. It has well understood theoretical properties. For example, it's a practical, all the reasoning about queries, minimization, query evaluation are all reasonable, practical. Okay, so the nice thing also about UCRPQs is they include recursive queries, right? So via a cleany star. So I'll give an example-based definition of what UCRPQs are, but I just want to highlight what's interesting about this for graph databases. So this has lots of applications in, say, reasoning about networks, so social network analytics, analytics on bioinformatics data sets, and so forth. So in gMark, we generate UCRPQs, and as far as we know, we're the first schema-driven tool to support recursive query generation in concrete syntaxes. So here's an example of UCRPQ. So in the Uniprot scenario, so the schema, suppose we're looking for each researcher, we're going to look up in their co-authorship network, right? So this is a recursive path query, walking over the graph, finding all the people that they've co-authored a paper with, or co-authored a paper with somebody, right? So some chain of co-authorship. So for all the people in the co-authorship, for each researcher, we want to pick out all the biological entities relevant to the proteins studied in the papers authored by people in that researcher's co-authorship network, right? So all the genes and organisms that are relevant to the papers in that person's co-authorship network. It's a very natural query. So kind of as a graph pattern, so the conjunctive graph pattern part is we want to look for x's have some relationship to some y's that have a relationship to these z's. And the z's are the biological entities, and the x's are the researchers, and the y's are the people in the co-authorship network. So here we need to compute this. We have a little regular expression, so we're looking at which papers are authored by this x, and who are the authors on those, and then we repeat. We kind of recursively collect all of these by crawling through the graph. And then once we find all of these y's, this is actually just a conjunctive query, right? So what are the papers? What are the proteins in those papers? And what are the genes and organisms relevant to those proteins? Right, so internally, this is just a kind of an enhanced data log language where the predicates can be regular expressions, right? So we're looking for this binary query, taking the transitive closure of the co-authorship network, and for those y's, just doing this disjunctive lookup of the genes. Right, so this is just kind of abbreviation to author by, reference by, encoded on, recursion, so it fits on a single line. So just some terminology. So this query has a single rule, right? So we can have a union, we can have multiple of these rules as long as they have the same output arity. Right, so this is a binary query, for example. This rule has two conjuncts, and the first conjunct has a single disjunct, right? There's no union in here. And the second conjunct has two disjuncts. It's a union of two different ways of looking up those biological artifacts. And within here, the regular expressions have path length 2, 3, and 3. Right? So there's path length 2 closed and path length 3. So this is just the structural information that we want to be able to specify in our workload configuration. Okay, so in a query workload configuration, the user can specify the number of queries to generate, and then the min and max number of conjuncts for each of the rules. We just randomly choose a number in that range. And then for each conjunct, the min and max number of disjuncts, and for each disjunct, the min and max path length. Right? So this is kind of the basic structural size, complexity of the query. We can also specify the probability to have recursion, right? So to tack on a cleany star. So maybe we want like 10% of all of our conjuncts to actually have a transitive closure tacked onto them. And also we want to associate a selectivity class, right? So this is like the expected asymptotic runtime behavior or difficulty of evaluating this query on a valid instance of the graph schema, right? So currently in this first release of gMark, we only support binary output queries because, well, we want to target regular path queries, which by definition are binary. And it turns out there aren't really any readily available tools. So the hardest, actually, in this project, for me, the hardest part of this was actually developing the machinery to reason about the selectivity of queries, binary queries, just using the schema, right? So we're not mining the instances for the behavior of structure. We're actually reasoning only from the schema. So this took a lot of work. So already that was enough, I think, in the first release, both for practical and also just a research effort to focus on the binary case. But clearly, we want to reason about the selectivity of higher arity queries in the future. It's already practical enough to reason about the selectivity of RPQs. We can also specify the distribution of the structure of the bodies of each of the rules, right? So the conjuncts, so whether or not we allow chains, stars, cycles in the body of the conjuncts, and star chain sort of shapes. You can also imagine other structures that we might add in future releases, like maybe bodies of very low tree width, right? So cyclic queries, which are a little bit more sophisticated than just a basic cycle. We have some more sophisticated structure, but still in a class that's provably well behaved from a query evaluation perspective. And then finally, we specify the range of allowable output arities, right? So are these Boolean queries, unary queries, binary? So we have specified the range of query arities which are allowed, right? And just to reemphasize, the graph configuration itself is also input to the query generator because we're generating queries that satisfy the specified constraints that hold on instances of this graph schema. Okay, so just in a nutshell, how do we go about generating our workloads? So we prepare what we call a schema and a selectivity graph, right? So this is just kind of like a graph representation of the graph configuration file itself, which is then annotated with all the information that we need to reason about the effect of navigating via queries over the edges, right, their properties. And then for each query to be generated in the workload, we'll generate a query skeleton, which satisfies all of the basic structural constraints, the shapes, the sizes, the complexity. And then we'll randomly assign a selectivity class to each of the predicates. And then we'll use these schema and selectivity graphs to instantiate each of the predicates by a random walk that maintains the desired selectivity of that piece of the query. Right? So really the most difficult part was assigning these selectivities, right? So this really required us to develop from scratch some non-trivial infrastructure for reasoning about the runtime behavior of queries just using schema information, right? We didn't want to touch arbitrary instances of this schema. Okay. So again, as I meant, just to reemphasize, in this first release, we focus on binary queries. So we assume it makes sense to talk about just three categories of runtime behavior, asymptotic runtime behavior of queries, of binary queries. So we'll assume that for a given binary query Q and arbitrary instances of the instance G, we assume that the output size grows as some factor of the size of the graph to some exponent alpha. Yes?
Can you explain what you exactly mean with a binary query?
Oh, one that outputs pairs of nodes. So the output is node pairs. So like the output of a RPQ is the pairs of source target nodes. So we're focusing on just supporting selectivity estimation on RPQs, essentially. So you can either have a constant number, right, so it's fixed regardless of the size of the input. Suppose we're just picking all pairs of countries and languages spoken in that country. That's a fixed, no matter how large your instance gets, assuming that your number of countries and number of languages are fixed, this is always a constant query. And then, so the next class up would be linear queries, right? So for, say, each person, their name, right? That's going to be, as you scale up the graph, assuming everybody just has a constant number of names associated with them, that'll be a constant query. And then quadratic queries. These are queries which touch and generate up to all possible pairings of nodes in the graph, right? So maybe in a social network, some pathological scenario, all pairs of people that are connected by some path. Okay, so we want to validate this assumption and also the estimation quality, right? So we assign an asymptotic selectivity class to each of the queries on the workload. And then we looked at this for a bunch of different types of variations of workloads on all of our 4 use cases, and looking at the asymptotic behavior on lots of instances and averaging it over many particular instances of instance sizes. And we found that those that were supposed to be constant were very close to being constant, so very close to 0. Those which were estimated to be linear more or less stayed around being linear, so closer to 1. And those that we estimated to be quadratic were by and large closer to an alpha value of 2, so as expected. These are just kind of really rough classes, but there's a clear kind of clustering of behavior across these 3 classes. So we think that the framework does a pretty good job of guesstimating the difficulty of query evaluation for binary queries. Okay, so we have our UCRPQs represented internally in some nice format. That's not any good because we want to generate queries which can actually be used by real tools. So currently we have a translator into 4 syntaxes. It's easy peasy to add another one in. So if you have another graph query language, we can plug it right in. So currently we supports Sparkle 1.1, OpenCipher, Postgres using recursive views, right? So that's how you would do a regular expression or an RPQ and SQL. And also Datalog for Datalog engines using left linear recursion. So this is what this query, our researchers and biological entities and their co-authorship network would look like. In Sparkle, it's almost a direct translation because Sparkle 1.1 has RPQs as property paths. And then OpenCipher and then Datalog, so we unfold the recursion. And actually, SQL and Datalog are the exact same thing. You're just writing it in a slightly different syntax. You fold out the cleany stars, just a recursion, a path recursion. Just a note, so how scalable is this? So on my laptop, this particular laptop here, I was just looking at how quickly we can generate these queries. So we can generate 1,000 queries in each of these scenarios. So bib is actually under a second, so tenths of seconds. The slightly more complex schemas on the order of seconds, and the really dense and the richer watt-div scenario on the order of, say, 10 seconds to actually generate the UCRPQs, and then to run them off into all 1,000 queries and all 4 syntaxes that we support for each of these use cases actually took about 1/10 of a second, right? So, and this is just on my wimpy little machine here, so it's not a bottleneck to generate very large workloads. Okay, that's basically in a nutshell what gMark is all about. We also did a small application just to study, so part of our motivation was to study the performance of current state-of-the-art tools on RPQ evaluation. So we did actually, there's a tech report if you want. You can just find it at our GitHub link there. You'll find a link to the tech report. We did perform an extensive performance analysis of 4 state-of-the-art systems under all of our 4 use cases. And it turns out that, well, our main finding was that recursive path navigation is very difficult for current systems, right? So RPQs. So this indicates really a need for further study of how we might engineer this basic class of graph queries on very large graphs. Okay, so just to wrap up, so our novel contributions to reemphasize. So gMark is about schema-driven graph and query workload generation. And one of the special features is instance-independent reasoning about the difficulty of query evaluation. One of the hallmarks of gMark is that we support fine control of query workloads. This is versus, say, designing, say, a query-centric approach where you focus on designing a handful of really well-thought-out queries. So these are kind of both complementary approaches for different use cases, I would argue. And as a side effect of this, we already discovered that there's some performance difficulties of existing graph systems on evaluating RPQs. And for more details, I welcome you to come by. We have a demo in VLDB this year, so we'll have a nice fancy interface to what is now just a command line tool. And so looking ahead, so Peter, you're already kind of asking, so some other features which might be nice. So looking ahead into the next release of gMark, so kind of on our to-do and or wish list. So in the category of richer queries, so currently all of our queries don't talk about individuals, right? So there are no constants, right? So we don't say from node 1, 2, 3, 4, 5, 6 evaluate this query. Just from some x to some y find this path. So that turns out to actually be an interesting problem in itself, how to maintain all the desirable nice features of gMark and reason about instances. So you have to kind of control the behavior of instances in an instance-independent way. It's a little bit tricky. Of course, adding more query shapes, I already mentioned. That's not really a research problem. That's more of just engineering and development. It would be interesting to extend UCRPQs. So, for example, say business intelligence workloads with say aggregate functions. That would be really interesting. So, how do we generate those and still reason about the asymptotic runtime behavior? And definitely extensions of selectivity estimation to higher arity queries. But I think it's a very, very deep and challenging problem that goes beyond just some master student projects. And then richer schemas. So this is what you're mentioning, Peter. So one minor thing is we don't require that all of the configuration parameters be actually present. So what are some natural defaults, right, for configuration parameters? And then schema constructs for a correlated structure, right? So and the SNB interactive benchmark There are correlations in the data. We don't support sophisticated structural correlations, right? So this is definitely something to add in a future release of gMark. And also things for particular application domains, for example, when you're generating, say, ontological graphs, reasoning about, say, class hierarchies. And also it'd be nice to, one of the, I guess the main reason for coming here and talking about gMark is to, say, talk about cross-fertilization from what we've learned and, say, alignment of with the LWC activities. Okay, thank you very much. Do you have any questions? Yes? Oh, I can show it to you. Here, I'll just take a really simple one. So it's as simple as it gets. I don't know if you can read that. Probably can't. Let's see. So it's just for each of the parameters. So we say, so this is we want I don't know, 1 million or 10 million nodes, some output format. So we have 4 edge labels, right? So just the author's type, published type, held in type. We have the distributions. So like 10% of the edges should be an extended to sort of relationship. We have the actual edge label, which is 3. This is just a human readable version of that. We have our node types. So in this schema situation, we have 5 node types of researchers, papers, journals, conferences, cities. And then we have the parameters of the relationship. So here we have from researchers to papers, we have the author's edge. Yeah. So it has a particular symbol. It's a Gaussian in distribution with those parameters and Zipfian out distribution with those parameters. So it's just simple, nothing special. I don't know. It's just the most natural thing you would think of if you start writing down these parameters. And here's the query workload. So we have a single workload in this case, 1,000 queries, the min and max number of conjuncts for each rule, the sizes of the disjuncts, probability for recursion, min and max arities, the activity classes that we want, the structures that we want, and the languages, the concrete syntaxes that we want to output. So nothing special. And I can show you, let's see, where would that be? No, but it'd be really simple to write one because it's a very, very simple structure. Trying to look for some queries. Here's an example of, so our output also follows a very simple, so we have a workload of queries, selectivity classes, just an encoding of the data log rules, and it's just, yeah, it's what you would think of if you started writing down a piece of paper in a way that could be parsed and passed around. Yes?
I have a question on the graph generation.
Yeah?
Something feels to me this is really complicated because you have node types, you have edge types,
Yeah.
right? And you have constraints. So if you generate a random graph, right, with papers, research papers, and authors, if you assign labels randomly, you will not satisfy the constraints.
Mm-hmm.
So do you first generate a random graph and then kind of adjust and chop off edges? Or
So what we do is we take an edge-centric approach. So we know how many nodes of each class we should have that's specified in the graph configuration. And then for each edge, it has a source class and a target class. And what we do is we just take those identifiers, actual or actually virtual. We do a random permutation, and then we just walk over these 2 lists. And for each node, we try to add as many edges as there should be of that type. And we do this by walking down the lists until we've hit the end of one of these 2. So it might be there's some stragglers on one of the 2 sides that don't actually satisfy the distribution. But overall, in the general structure of the graph, you do see that distribution of values, but there are exceptions at the end. Yeah. So it's really just, we just go through and we just use up our budget of edges, and we do this edge by edge, and then just randomly associating edges between instances of the source and target class.
I have a question about the evaluation. I actually just pulled up the paper and I was curious. Can you comment more on the actual results? Because I'm looking here and just as a quick look, it seems that for recursive queries, everybody failed except the data log one, and then for the linear queries, for the constant and linear, sorry, for the non-recursive one, for the constant linear, Postgres was always better. Quadratic, the Spark ones. So I'm just curious, that was a quick observation. Can you comment on what's going on?
Yeah, so it's a little more nuanced than that, so it's not always Postgres, but the summary of all of those experiments is that they are all surprising results. And if you want to talk about some detailed part of it, we could sit down and talk about it. Yeah, but by and large, all of the results were surprising, so we triple checked everything to make sure that we were really seeing what we saw. If you notice all those graphs, so we only go up to graphs with 32,000 nodes. That's just because we couldn't get systems to complete those queries on larger graphs, so I shouldn't say anything. But it's in the paper, we can talk about it offline.
One more question, sorry, I've already too many questions here, but okay, so you see that more kind of realistic generation of data it's on your agenda. That's positive. But I don't actually understand. You say you don't want to do something with instance-based workloads, or what do you? So something with instance, but you want to avoid instance awareness, or what do you mean with that?
So we want to do all of our reasoning from the schema.
Okay, and is that possible or desirable?
So far, it's possible. I think it's what we show. And is it desirable? I think it's desirable for at least two reasons. One is the schema is much, much, much smaller than an instance.
But the reality is not like that, The instances count a lot, actually. So, if you want to have this benchmark any meaningful, these results may actually not be meaningful at all. And also, you can put more advanced data generation on your agenda, but you also should couple that then with an awareness of that in the workload generation, because queries interact with that.
Yeah. So, our goal was to generate queries with understandable behavior for valid instances of the schema. So our assumption is that all instances in the world have some structure in them. Right? Otherwise, it'd just be random noise, and it wouldn't be actually very interesting as an instance. So assuming that there is structure, we want to reason about the behavior of queries to the extent possible based on the inherent structure of the data. But indeed, sometimes you want to talk about individuals, like individual people or individual things in a graph. And so our current challenge is, to what extent can we still do that without having to generate a whole instance, or looking at the whole instance. So that's essentially just for practical usability of the system. And there's a second reason that it's desirable to try to avoid touching instances is if you can explain a query in terms of the structure of the instance, then I think it's much more understandable and explainable than, well, this is just person XYZ, and they just have this weird structure. But that doesn't tell you something about the domain. So yes, I completely agree with you.
No, you don't.
No,
You do not agree with me.
No, I completely agree with that.
You think that you can get away with actually ignoring relations between predicates in the queries?
So we're talking about.
Because then you're kind of you cannot only do that with the schema. Okay? The actual values in those predicates interact with the value distributions and the value correlations in your data.
Yeah. So no, I disagree with you that I'm disagreeing with you. My challenge is to the extent possible, how far can we go reasoning at a structural level?
Not very far.
I think we've gone quite. I think so. So I think we've gone quite far. And as I already mentioned twice, on our to-do list is to introduce schema constructs for talking about. You have a general description of correlated behavior. That's a schema. That's a high-level description of structure of instances. So we want a construct that allows us to specify this. So it's like we have this correlated structure between these edge types that we want to hold for any valid instance of this schema. So definitely, it's definitely on our to-do list to look at larger term correlations beyond say, controlling the in and out degree
It would
distributions.
be very interesting to use like your version of the SME data,
Yeah?
and then use a few of the SME interactive queries and see and compare them with,
Yeah.
let's say, a correlated version of that.
Yeah, so the big-
Because the data generator of the workload generator actually does these things. You know, so it has used the same template. Then it takes like 2 query parameters which are either correlated or anti-correlated, and the plans that you need to solve those two same queries but with different parameters, they are really different.
Yeah, I completely agree with you. So as I said, that's definitely on our to-do list, is to add these sorts of correlations between
Yeah,
structural.
but it will not
structural.
only be something in the data generation, it's also it will affect your selectivity
Yeah.
analysis,
So
and
the-
the query workload generation.
Yeah, so the question is, how do you choose individuals that have the desired runtime behavior based on this correlated structure? That's the challenge for us. So how do we support this without having to delve into, looking at a bunch of instances of the schema? But from the schema level alone, that's our challenge. It's not that we're ignoring instance behavior.
I can point you to, there is a paper actually written by Andrei Gubichev. We might try to generalize this. Who knows?
Yeah, so it's definitely one of our top priorities is to add correlated structure. But we still want to challenge ourselves. Can we do this without having to do data mining on instances?
No, sorry, that's what the Gubichev paper does. Yes.
Yeah, so that's our challenge. So can we do it on this much smaller thing? Is there some reasonable schema construct that allows us to specify and reason about correlated structure? And I think it's that's an interesting challenge. And that's the challenge we've posed to ourselves. So I disagree that we don't disagree. I think we're in complete agreement.
Good.
Of course, it's all about instances in the end. Yeah, but it's just we assume that there's structure in these instances. If there isn't structure in the instances, I mean, what is there to do?
All right, let's thank Joyce.
Thanks.